Oh my god, why would you? Dude, you could have taken like what is it, that film class.
It wasn't offered that semester. I don't think it was.
I'm so sorry. That class is such a joke. It's
One of my
amazing.
friends took like music appreciation.
Okay, everybody's online today.
But apparently this one
Question,
professor, she only had a
Yeah,
choice
it's
of
concerning
listening
about
to- She said that she sat down to listen to jazz music for 45 minutes and left like
C228.
half an hour before I got to and I had no homework.
Yeah, that sounds exactly like it.
She said that was Lou's
Yeah.
show up, listen to music, and
Okay.
halfway.
And you want us to,
I don't know, at hindsight, I don't know why. It's like,
you want us to spot
So much eating.
section of the.
I was me and Jack were looking at trying
But, like,
to
what
get
is
that,
the
and still
other
reference
extra?
what we did in that class, I'm like, hilarious.
Oh, that's just an example.
This is example. You have to do probably the same thing in math.
Okay.
This is example I
He was
use
the one that
Excel.
was meeting with me and Jack.
So this is the same in
Me and Jack are all friends.
This is example using Excel.
And
Numerical integration method.
lifestyle.
It's essentially the same you did in project E2B test 3.
Does anyone do the note that-
The only difference is you integrate from 0 to 1, not the minus 1 to 1. That's the only difference.
And no
Nothing-
using LightScript, right?
You did your own project. What are you talking about?
That- No, like,
I don't know.
LightScript will make it look nicer. That's
I don't care if you want to use TypeScript, use TypeScript.
okay.
You did your project. Anyways. Now, you want to use TypeScript, that's fine. If you want. Anything else? I mean, why do you want to use TypeScript?
It's just PDF.
It looks prettier, that's the reason of engineering? No way.
It's more aesthetic.
No. You want to use TypeScript because you want to do symbolic math. That's the only reason. Because it looks prettier. It's not engineer's reason. No. Sorry. Please act like an engineer, you know.
So basically, he had more than a script in the lines.
Okay. Anyway. One person online today. Can you hear me?
Yeah.
Okay. I'm gonna mute you for a moment. Okay. So let's take the in-class attendance. All right. This is a new camera. So I can take video.
Yeah.
Present next class? Huh? You ready to present next class?
Any other question before we begin today? Okay, a few updates here. Tomorrow I cannot have office hours. It sounds crazy, but I got Senate meeting. I'm faculty Senate of College of Engineering. I don't know why, but I am. And then we have a big faculty Senate meeting. If you want to bring some complaints, a big complaint to the school's admin, I can hear. Because I'm technically speaking, I'm COE faculty Senate. Do you have one?
I could get you a list.
Okay.
I would be happy to get you a list.
If that's the case, you're gonna
List,
need more than
not the
a
one.
piece of paper.
Okay.
Okay.
I think one concern I have is I keep taking the in-class attendance video and keep track of everybody sitting where kind of thing. No one uses it this semester. Why am I doing it? That's a big question at the end of the semester. No one approached me and asking that kind of question, why am I doing it every single semester at the beginning?
Apparently, other professors, they've been contacted a lot about theirs.
Yeah, it's happening.
No one contacts me. I don't know why.
I guess we're not sick.
Well, because I usually do not respond nice.
Yeah, that might be why.
I guess you know me. I'm a person, if you ask like unreasonable things, I respond unreasonable way. If a wellness center says, oh, you know, you have to take every single class attendance and class chart, I always say, why? Do you actually use it? And then how often do you use it? Can I see the data?
That's not for you to know.
Why do I have to sacrifice every single class first 5 minutes? Do you want to pay back the tuition for students? Those kind of questions. I'm not gonna give you a nice, oh, okay, of course I do. I'm not gonna say that. If they ask me stupid things, I'm gonna respond. There's so many stupid people doing stupid things here.
Amen.
Amen to that.
Amen.
So again, if you do great things, I will respond great way, because this is engineering class. You guys are the only people who actually can think. Okay? That's why people pay you real money. Okay. All right, so let's move on. So tomorrow, again, I cannot have officers. And also, don't forget, this is end of the semester announcement. Of course, you know, end of the semester course evaluation, always the long term, you know. In my mind, this is like a feedback. It's not evaluation. Why on earth you evaluate me? You give me feedback. That's all I want, okay? So this is a wrong English term, but anyways, people use it. Oops, did I say bad things? Why are you so quiet? In reality, this is feedback request.
Yes.
You don't evaluate me. No,
That's your boss's job.
I'm boss.
Oh, there you go.
I make all the rules here.
There you go. There you go.
I try to do always things that really making sense. I don't want to do anything which doesn't make any sense to me. In other words, giving passing grade for those people who has no clue about it at all. It doesn't make any sense to me. That's why I don't do it. But if you work really hard to try to understand things, yeah, of course, I don't want to go harsh. I don't want to flunk anybody, quite frankly. If you stayed until this last minute trying to do everything, at least you deserve C. If I don't see your face here, I don't know what to do, but okay. So anyways, especially for those like a borderline A and B, I hope you keep A. All right, so that's why I'm doing this. Lowest score drops. Okay. So again, for those people on the borderline, this may impact fairly big manner, so please don't forget. So what I want is your feedback. Of course, something worked really good, I want to hear because I want to continue doing it. And then there are certain things that, hey, you know, this is not useful. I wish you would do this way better kind of thing. It's not like, hey, I hate you. I hope you go to hell kind of statement.
That's what
you know,
late night
people write
professor
that.
is for.
People do that kind of stuff. That's kind of fun reading, but you know, it doesn't help me at all. It doesn't. People write those kind of things, which is kind of fun. Oh, look, this person hates me. There's one person actually years ago wrote me saying, hey, he's a Nazi. He does everything in his own way. I'm Japanese, by the way, okay? You cannot call me that. But anyway, it was fun reading those kind of conversations. But bottom line, it doesn't help anybody at all. It helps you release your stress, but too bad. Anyways, so please follow through the simple procedure. That's it. And also, end of the semester is going to coming up. This week is end of the semester week, and then Friday midnight semester ends. So that means midnight of Friday, December 10th, I'm going to cross out the canvas. Okay, it's actually automatic. It's automatically closed out, so you cannot access to canvas. Now, of course, all the course materials here is all listed in my course homepage. I'm going to keep it up in this course homepage until the beginning of next semester, so you can continue accessing it. And also OneDrive, I'm going to keep it until probably next semester, beginning of it. So you can actually access to your graded materials continuously. Okay. However, you cannot accept the final exam. Final exam, you never know. Okay. Sorry about that. I guess I have to keep some component proprietary because it's going to allow people to kind of take up an opportunity to negotiate whatever it takes. I don't take that negotiation. Go ahead.
You mentioned in the syllabus a plus or minus 1%.
Yeah. Yeah.
Adjustment.
Yeah.
I assume we won't know about that.
It's usually +1 automatic, usually. Unless you feel, wait a minute, Dr. H has certain feeling against me. That means something very severe. That means, I don't know, you cheated, get caught, spent like 3 hours talking with Dr. H. And then he gave me released but with tears kind of thing. That's usually not the -1, even 0. That means I don't feel like I assist you 1% to boost you up from B to A kind of thing. I don't want to do that. But still, if you earn B, B is B. I usually do not deduct -1. -1 is, have I ever done that before? I cannot even remember. Usually +1. Okay, I say things, but usually say things. That's it. I don't keep it in my mind kind of thing. Well, I really hate robot kind of thing. No, I don't hate you. Okay, you're a great guy. I really mean it. Okay, it's just a joke. Don't take it seriously. Any other question? So usually +1 automatic. Again, bottom line, I don't want to flunk anybody. As long as I see your face in this classroom today. Okay, last week you survived through it. So go ahead.
I was going to ask for the homework for C2.
Homework C2, yeah. Go ahead.
You had it up earlier, C2-2A.
C2-2A. C. Yeah. Okay.
In your example, what's the average CPL minus CPU?
You take those two and then take the average means, when you compute this rectangular shape, this height, that height, different. Take the average to make a rectangular shape. And take a look at the project document, project 2B, task 3. Take a look at it, okay? That actually tells you what it is. Suppose you worked on it. Okay, all right. Yeah, why average? Well, because.
I think it's in the handout. Hints.
Okay. Hints. Here we go. So you are taking average between those 2 points. That's what it is. Okay. So this is called central differencing scheme, because you're taking average between this data, that data. If you take only this data, it's a forward difference. If you take this data, it's backward difference. If you take average, it's central difference. Anyways, okay, any other question? Okay, so today, I have a plan for Wednesday's class, so let's just talk about that. Wednesday, I'm going to have a special session on Wednesday. Okay. Oops. So Wednesday, Zoe and also Stephen shows up and then basically gives you demonstration of how to use X55 and then trying to show a little bit more that they're doing something real. So they're going to show something that what they're doing. So I don't want to give a limitation of time. So if they want to take over entire 50 minutes, I'll let them do it, no problem. But because of that, okay, the other section, section 1, which is 2 p.m. class, I will do a regular lecture, and then regular lecture means I'm going to finish up unit D11, okay, in section 1. So I'm going to post the video of a section 1, and then section 1 people can look at their presentation. So it's almost like a, crossover the video lecture. So that's the Wednesday, okay. I'm going to post both sections video. Go ahead.
Can we go and attend in person the 2 p.m. class section?
You can if you want to.
Okay.
If you don't want to go through the video, that's fine. You can show up. That's fine. Location is location is on the home page.
B50.
B50.
Lower, the course information.
Yeah, that's right, B52B. That's the section 1, okay, 2 p.m. If you want to show up as in person, that's fine. Yeah, I'll welcome you anyways. And then video will be posted, okay? So that's my plan. Wednesday's class will be kind of covered in different section and videos posted, okay? And then the other section actually is going to finish up D11, but they are not exposed to the Xprior 5 demo. So Xprior 5 demo is going to be videotaped, and then they see it.
Oh boy.
So your demo is videotaped.
Yay.
If you screw up, that's okay.
No pressure.
If you screw up, I basically erase the video. So pretending like nothing happened. So the other section people don't need to know. If you screw up so bad, yeah.
I have friends in the other section that would give me so much crap for that.
No, I mean, it should be all right. It's a simple video. I mean, simple software. Okay, and then whatever the time remaining after those demos, I'm going to show you whatever I can do, and then conclude the semester. So let's move on today. Let's take a look at class example problem D11. Okay. Okay. So from the previous lecture, I guess we now know that we can determine after you design your 3D wing, you can determine total drag coefficient of a 3D wing. 3D wing total drag coefficient is addition of a 2D cross-section profile drag plus induced drag component. This is the additional component after you design your wing. You're going to add up this additional component, induced drag. Oftentimes, this is called viscous drag. This is called induced drag. Viscous drag is drag due to viscosity, and then oftentimes called parasite drag. Okay. The other one is a drag due to lift. So people use lots of different words to describe the same thing. You have to get used to it. It's aerodynamics. It's lots of slangs people use. So today, important thing is, so since these are coefficients, you can add them together. One is 2D, one is 3D, but it's okay because it's dimensionless. So that is the way we are going to estimate the total drag coefficient after you design your 3D wing. So let's consider one example. In order to simplify, I purposefully choose only wing kind of airplane. This is the flying wing. There's no fuselage. So in reality, if you design conventional airplane, you're going to pick up the fuselage. Fuselage is going to give you some negative effect. In other words, you're going to lose the lift produced at the fuselage section that is going to lower your wingspan efficiency and then comes up with higher drag. Okay. So this is like a simplified approach. This is the flying wing. Okay. Wing area 200 meters square. This is the wing platform, obviously. Okay. Do you remember that from A5? This is the wing platform area S. This is 200 meters square. You are going to drop your airplane to the ground, and if you take a look at everything from above, how much wing area do you see? That's called the wing platform area. Go ahead.
Yeah,
Yeah.
can that go as like,
This is 100% subsonic flow, Mach number 0.5, yeah.
okay, so it can't like go past the barrier, like the,
This
the
airplane,
wings are ripped.
this airplane can go supersonic probably, I guess, but it's not designed for it.
The 26 Raider, that's gonna be the supersonic version.
Yeah.
This one can't.
I don't think this one can.
So there's a supersonic version of designed airplane like this, but this is probably not designed for supersonic. This is the stealth is the main thing.
Okay.
This is mainly operation-wise, it's a subsonic airplane. And then this problem is a subsonic problem, 0.5 Mach number, 10 kilometer altitude. This is a level flight. Weight is given 7.5 times 10 to the 5th newtons. I'm nicer because if this is final exam, I give you kilograms. What do you mean? Go ahead, question.
What is the span efficiency factor?
Span efficiency factor is this thing.
CD.
This is a span efficiency factor. If it's ideal, E equal to 1. Okay? All right, so E is given. Go ahead.
In the, you said you would give us kilograms in the final. Would
Yeah.
we just multiply by 9.81, or do you want us to use the?
Kilogram is a kilogram. Do you know how to do it?
Kilogram, I don't know.
As a
Kilogram.
mass or as a? Would you give it to us?
The
as a
weight
mass
of
or-
the airplane, 1,000 kilogram. What do you mean?
1,000 kilogram force.
Something like that.
And
You
then
can figure it out. I'm not gonna cover that kind of unit A1 material. You know that. Kilogram. Well, I can possibly use kilogram, which is a completely non-standard unit use. Okay, so you have to convert it to newtons. So, anyways, so this is a level flight. Lift equal to weight, so weight is equal to lift. Okay, and then minimum profile drag. What do you mean? CD min. So this is usually the condition for level flight, okay? 0.5 Mach number, this is a free stream Mach number, M infinity. 10 kilometer altitude, that means you can use probably standard 10 kilometer altitude conditions of air. Let's estimate the total drag on aircraft. Total drag is drag. In order to have a total drag, you have to have a total drag coefficient, okay? With the flight condition and 10 kilometer altitude, you can determine actual drag force, okay? Let's find out. So this is lots of information is given here. First of all, NACA 4412 airfoil. So this actually gives you some information. This actually gives you what is the estimated CD min. Next page, let's take a look at NACA 4412 airfoil data. Now, this airfoil data is coming from the low-speed wind tunnel testing, right? And then this is high-speed flight. So if the Reynolds number goes up, what is the effect on the drag coefficient? You can basically tell that, okay? So there are multiple plots of drag polar. First of all, this thing is something different. This is the Reynolds number 6 times 10 to 6 with a standard roughness. So this is rough surface. The other one is a standard surface. And then this is the lower Reynolds number. If the Reynolds number gets higher and higher and higher, it seems like drag polar starts to converge into certain locations. So that means higher speed is actually better for drag coefficient. So from that perspective, even though this Reynolds number doesn't match up with 0.5 Mach number, of course, your airplane's actual flight Reynolds number is much, much higher than that. However, you can tell, basically saying from the low speed testing, perhaps minimum CD, you can estimate. Probably slightly less than that, but we can safely estimate it's around this value. What's the value? 0.006. So let's start from here. This is not so far away from 0.5 Mach number. You have to reason it though. This is a low speed wind tunnel testing. You can never go to 0.5 Mach number much up. However, drag polar seems to converge into this location for higher and higher and higher Reynolds number. You can tell those kind of things by running X prior 5. Isn't that correct? So
Yes, it is.
yes, it is. That's right. So you are going to get those kind of knowledge by running X prior 5. Go ahead.
Did you like calculate CL already to be able to know what it is?
How do you, calculate CL, but that CL is an airplane's CL. This is not airplane. This is airfoil. Okay, so this is lowercase.
Right, but like how did you know what the
This is a section CL. There's no such information given. You only know lift of a wing, not the cross section. No. You cannot compute the lift of a wing. Well, you are given lift of the wing. This is a lift of the wing. 7.5 times 10 to the 5th Newton. This is the wing's lift, not the section lift. You have to differentiate clearly those two. So first of all, one thing you can get is a CD minimum is 0.006. This is estimated from NACA 4412 airfoil. Okay, estimated from NACA 4412 airfoil. Obviously, this is Reynolds number, highest possible value, 9 times 10 to the 6. Obviously, this doesn't match up against the 0.5 Mach number. 0.5 Mach number comes with higher Reynolds number. However, if the Reynolds number increases, the value seems to be converging to this value. It is not so bad estimated value. Okay, so next, what else can you say? You know the rift of the wing, rift of this wing. Capital L, be careful, this is capital L, okay? So lift is equal to weight, which is 7.5 times 10 to 5 newtons. This is a rift. What else can you do? So Dutimi, do you have a question for this? Do you keep asking rift, and this is a rift of a wing.
Well, because like, I just don't understand like the estimated CD min. Is it just like where the values converge?
CD min is determined because you chose this particular cross section. Because you choose NACA 4415, minimum profile drag.
Oh, is that?
Because that's what you choose when you do like a rubber flight.
Okay.
What is the minimum here?
Okay,
Yeah, that's what I'm choosing first. Okay.
yeah.
Isn't it also based on where the CL, what CL is given? Because
CL is usually around here because this is a cambered airfoil, but this is section CL, right?
Yeah.
This is the wing. Which section are you talking about, kind of thing? I'm trying to find out minimum profile drag because I need to find out total drag. Section lift is not something I'm interested in.
Okay.
But the airplane wings rift is given here. This is a rift producing out of this wing, 3D. Okay, this is 3D. So from here, let's just pick up the 10-kilometer standard altitude. Density of free stream. This is a standard, 0.4135 kilogram per cubic meters. Okay. So if you know the temperature, you can, of course, get speed of sound at this 10-kilometer altitude, gamma RT infinity, square root. So this is going to be given 299.5 meter per second. So this is a standard 10-kilometer speed of sound. So Mach number 0.5 means you are moving with this airspeed. This is 149.75 meter per second. So this is your airspeed of 0.5 Mach number. This actually gives you free stream dynamic pressure 1/2 rho v squared. Okay, 0.4135 kilogram cubic meters, velocity 149.75 meter per second squared. This is going to be 4,636.382 Newton per meter squared. This is Pascal. Okay, so this is the dynamic pressure of the free stream. So why am I doing this? Now you can determine lift coefficient, right? L over Q infinity S. So you can determine lift coefficient of this 3D wing. This is capital 3D. So this is the wing lift coefficient, okay? That's something I'm interested in, not the section lift coefficient. Wings lift coefficient, 3D, okay? So this is lift, we know, 7.5 times 10 to 10 to 5 newtons. Q infinity, 4,636.382 Newton per meter square. Wing area, 200 meters square. Okay. So now you are going to be given wings lift coefficient 0.8088. Question, go ahead.
So is 3 for big CL and 2 days for like the little CL and the L final?
Again, little CL, I don't care about this case. I'm talking about airplane.
Yeah, I was just talking about the difference.
Difference is little CL is an airfoil. In other words, depends on your shape of each cross section. This is section lift coefficient.
Okay.
Big CL is a wings lift coefficient. Those are completely different. Now, I'm not interested in this thing. However, we need a profile drag because we are estimating total drag. Total drag is addition of profile drag and induced drag both. Okay, that's why. Okay, so now, so because of that, you can determine CD. CD is equal to CD, which is a minimum value. This is because it's a level flight. You assume that you are flying with minimum CD condition. So this is a profile drag. So profile drag always exists, even though, okay, you are not even producing lift, right? Why is that? Because this is essentially viscous drag. So when you run X-Flyer 5, you're going to be given two different kinds of drags. One is a viscous drag, one is induced drag. As you pitch up your 3D airplane, obviously induced drag goes up. Viscous drag goes up a little bit, but mainly induced drag goes up. I hope those two guys show us the demo for those. You can visualize those, right? Of course. So that's the profile. This is a viscous drag component. Okay. I think you probably need to visualize to understand. So this component, viscous drag. Viscous drag is always there because when you choose your particular cross section, this viscous drag comes into play. You cannot avoid it. But the other one is, of course, drag due to lift or induced drag, CDI. This is called induced drag. So induced drag is, of course, as the name implies, this is the drag due to lift. So as you pitch up your airplane, producing more lift, it is going to increase also the induced drag coefficient, okay, due to lift. So you are going to differentiate those two different kinds of drag components. That is going to compose of the total drag coefficient of your airplane. So one of the important things about X-Flyer 5 is you can actually literally visualize those, okay? So let's expect high on Wednesday because those two guys actually going to show you how to visualize those two. It's actually cool. That's one of those great benefits of using this software. You can visualize what kind of drag component you're going to produce. And then that component is coming from pressure distribution and also separation of the product, right? Okay. So everything is based on what we covered in this aero class is going to be inside of your software. So let's just finish up next page. So CD is equal to CD plus CDI. So we are expecting minimum, this is 0.006 profile plus. This is going to be capital CL square over pi E aspect ratio, which is 0.006 plus wing lift coefficient 0.8088 square, pi times E is 0.95. Aspect ratio is 10, kind of low aspect ratio, in which this is going to be 0.028. Okay. So interestingly, it's about, which one is higher? This is higher or this is higher? This is higher, maybe. Okay. So for the airplane to maximize, was it range or endurance? I can't remember. For the airplane to maximize range or endurance.
Endurance is in like,
Is time, range is just distance, so they're pretty much the same.
If those two are equal to each other, which one was it?
Range.
I can't remember, even though I told flatmate last time. So if you see CD equal to CDI, in other words, parasite is equal to induced, that is going to maximize, I think, range or
It's
endurance.
range, that's what they use for gliding.
That's a grading, so that means maximize what? Range. I
endurance.
trust you. I have to
Endurance
go
is
back.
more of
to
a connotation of like total service life.
Yeah, that's fine. So I have to kind of go back and take a look at FlightMac materials, but it's one of the conditions to optimize flight. Okay. So the airplane pilots knows that in order to maximize range, you have to have a flight condition which is a parasite drag is equal to the induced drag coefficient. That actually rock set your angle of attack and based on the flight speed and then Reynolds number. Okay. Anyways, those are the kind of things for the next class that you start taking flight mechanics. Everything starts from direct polar. Here we go.
Sir?
Direct polar. This is important. In other words, X prime 5's purpose is to create this direct polar for your airplane wing. This is going to be a starting point. Okay, this is how much your airplane can perform. Then this is going to determine what kind of engine you need in order to have this much endurance and range. And then what is an optimum condition to optimize your range and performance? Okay, range endurance, other things. What is it, Robert?
Oh, AR, is it, did you,
This is aspect ratio,
oh,
which is 10.
okay, sorry, I almost got it mixed up with the Chinese kilometers altitude.
Any other question? Yep.
Yeah, so like finite versus infinite range, like finite is just like an area that's not infinite.
Okay.
Like for a finite.
Finite is a 3D wing.
That's just not like,
Okay.
that's thinking too much about it.
So that's all the way to.
Yeah.
Here we go.
Yeah.
So this is a finite 3D wing.
Yeah.
So this is airfoil's definition is if you have infinite wing and cut off with a unit span, that's called airfoil. Okay. Any other question? Can I move on? Go ahead.
Okay, this is probably very silly, and if you just say anything that does, that's okay. Like, how do
Yeah.
you calculate Reynolds number?
Reynolds number.
What do we do ever get?
Sorry, that's the record you're listening to.
Reynolds number is density, airspeed, in this case, code ranks divided by viscosity. Reynolds number based on the code ranks,
Okay.
if so. Reynolds number could be computed with lots of different normalization factor, which is, this is a characteristic rings. Reynolds number of a boundary layer is, this is actually boundary layer height. If the Reynolds number within the pipe flow of a water or something, it's a diameter.
Okay.
Yeah. Okay, anyways.
Thank you.
Any other question? So you need the viscosity information. So next page is, this is actually quite important. Now, one of the adverse effect, in other words, you're going to design a wing out of your choice of your airfoil. Now, you're not going to expect the wing to perform exact same way as you design your wing. First thing, of course, you're going to introduce induced drag coefficient. The other one is, of course, the lift curve is going to be reduced. So why is that? Lift curve is reduced. Big reason is because your angle of attack is reduced. Okay, remember, the downwash is going to induce alpha I. This is going to effectively reduce your angle of attack. So with the same 5 degrees of angle of attack, if you take a look at the NACA chart, because you choose the NACA, well, 5 degrees of angle of attack is supposed to produce CL equal to 0.7. So if I create the wing and then pitch up 5 degrees, I'm going to expect lift coefficient 0.7. No. No. So lift curve slope, do you remember that? Is going to be reduced. This is 2D airfoil lift curve slope. This is going to be reduced as you create a 3D wing. This is a reduction of lift curve slope. Okay. So it is actually this equation. So this equation, I'm not going to spend time deriving it in class. Basically, I gave you all the details. But this is going to be one of those homework assignments. You have to derive it by yourself. Anyways, so this is the equation relating to the airfoil's lift curve slope. By the way, interesting question. What is the typical value for this? What is A0? Somebody please tell me. 2 pi per radian or 0.11 per degree. Yeah, this is a typical value. If it is thin airfoil, this is the value. Okay. So oftentimes I give you thin airfoil with 2 pi per radian lift curve slope. Create the wing with this aspect ratio, this taper ratio, this and that. What is the actual lift curve slope of your wing? Okay, that is going to be way less than this original choice of your airplane's airfoil. Okay, so in order to produce the same lift coefficient, you have to pitch up more. Too bad, because your effective alpha is reduced. That's why.
Is the lift curve slope always constant?
Lift curve slope is not a constant, but you can consider it's almost constant, which is linear. What is the lift curve slope, by the way, Robert?
It's mentioned in the last section. I forgot. I know it's like.
This is a lift curve slope, isn't it?
Yeah. Yeah.
So we oftentimes consider this is close to linear. That means constant.
Okay.
But in reality, if you introduce thicker and thicker cross section, it is going to be probably non-linear.
Yeah, it's gonna be negative.
Yeah, that's right. So, but again, let's assume thin airfoil. So this is close to pi 0.11. Anyways, so this is the details of derivation. And also, if you come up with low aspect ratio wing, what is it? Low aspect ratio wing? Have you ever seen that kind of airplane?
Stuffy wing.
Right next to the bookstore.
The Starfighter.
Yeah, this is low aspect ratio wing. That's actually three-ish aspect ratio. If so, it actually further reduce the lift curve slope. So that airplane is pretty bad in low speed. Okay.
Yeah, that's why you call it a rocket.
And also, if you have a wing sweep, do you think it looks cool, but do you think it is going to make a better airplane? No way in low speed. In low speed, this kind of airplane is terrible because it is going to further reduce lift curve slope. Okay. So again, those are the corrections of a lift curve slope further reduced.
So that triangle airplane.
Triangle airplane is terrible in low speed.
Okay.
Do you know why triangle airplane is a preferred?
Is that the swept wing?
It's also radar.
I think I have a handout. Let's just take a look at the delta wing. Is a delta wing handout? Possibly.
Comfort deck?
This is a delta wing. So you can take a look at it if you want to. This is actually designed for high speed. Okay. I'm talking about tailless delta. It's not like a half. Tailless delta is like a garage. Okay. Anyways, I'm not going to cover this in class, but you can take a look at it. This is a delta wing. Okay. This is not good for low speed. Anyways. This is mainly designed for high speed.
Is that the low wing aspect ratio?
Yeah, it's a slender low aspect ratio wing. Delta wing. Okay.
Oh, the double delta wing. That's fun.
Yeah, that's right.
The dragon.
Okay. I hope that since this is a high-speed airplane, Aero 2 professor should cover those. Okay, hopefully. What's that response?
Whenever some professor says that they should cover it, it's, you jinxed it. They won't cover it now.
Well, I'll be happy to share whatever I know. But anyways, so the point is being, if you plot lowercase CL to alpha, so this is a 2D airfoil, is that correct? So 2D airfoil behaves like this, with lift curve slope A0. However, if you create wing, which is now you're plotting CL against alpha, curve is reduced. Okay? So suppose if you pitch up like 5 degrees and then you expected 0.7 with the same 5 degrees, now you are expecting less than 0.7. So the lift coefficient is going to be reduced effectively. The reason here is if you plot capital CL against alpha effective is alpha minus alpha I. Now you are going to represent, this is the original A0 lift curve slope, but now this is going to be reduced. So that's the reasoning behind this equation relationship. You're supposed to derive it in your homework assignment. Derivation process is all fully explained. So in this class, I want to take a look at this example problem here. Okay. So let's consider a wing with an aspect ratio of 10. Yeah, this is 10-ish aspect ratio, A10. With NACA 23012 airfoil, this is actually portion, I think the root section of this airplane is NACA 23012.
It's up to that first pod where the gear.
Something like that, yeah. I remember. Assume that the Reynolds number is approximately 3 times 10 to 6. No, this is only assumption. I don't think so. But anyways, 3 times 10 to 6 to make your life easier. Span efficiency 0.95. This is probably too high, but anyways, this is E. Okay. If the wing is at the 4 degrees angle of attack, let's calculate the lift and drag coefficients of the wing. In other words, I want CL, I want CD, both capital. Okay. So if this kind of problem shows up as a final, where is the starting point? You start, of course, always from 2D cross section to begin with, just like what you use. Just like when you use X squared 5, you start with 2D cross section. So first question is, what kind of cross section or airfoil does this airplane has? This is NACA 23012. So next page, it's given NACA 23012 airfoil data. So I'm going to probably pick up alpha zero lift right here. This is alpha zero lift. Is, let's say, minus 1.5 degrees. And then 4 degrees alpha is right here. This is alpha equal to 4 degrees. CL is, what's the CL here? About 0.5 something, 0.52-ish maybe, I would say. So those are the data set you're going to read off from the actual data of NACA 23012 airfoil. Okay. So from here, I'm going to estimate lift curve slope. So this is 0.52 minus 0 divided by 4 degrees alpha minus alpha zero lift is minus 1.5 degrees. Let's say this is alpha zero lift because CL is 0. So this is going to estimate your A0 lift curve slope 0.09455 unit is per degree. Now you want to convert it to per radian. Multiply by 180 divided by pi. This is going to give you 5.417 per radian. Be careful about that because the equation is all about radian based. So pick up the equation. So this is the 3D lift curve slope wing. Is equal to A0 divided by 1 plus 5.417 per radian divided by pi times E is 0.95. Aspect ratio is 10. So this is airfoil. 2D. Okay. So if you compute this, this is going to give you 4.585 per radian. Let's convert it back to per degree, multiplied by pi divided by 180. This is going to be 0.08 per degree. So this is much, much less than the original thing, right? This is reduced, right? So from here, you can compute a few things. First of all, lift coefficient, CL at 4 degrees. CL is A times alpha minus alpha 0 lift, which is 0.08 per degree divided by 4 degrees minus 1.5 degrees. This is going to be 0.44. Okay, now, so this is the lift coefficient of this wing. Now, CD, you can get CD out of section lift coefficient. Section lift coefficient 0.09. I'm sorry, this one.
Is that alpha not?
Let me finish, okay. So 4 degrees angle of attack, 0.52 here. Let's read off drag coefficient. So CL 0.52, CD is what? 0.006. That's the CD corresponding to this CL value here, 4 degrees. Okay. So now let's just use that. CD is equal to 0.006 because CL is equal to 0.052, sorry, 0.52 at alpha equal to 4 degrees. Okay. So now CD equal to CD plus CDI. So this is 0.006 plus. CL is 0.44, right? So 0.44 squared divided by pi times E is 0.95. Aspect ratio is 10. If you compute it, this is going to be 0.012. So this is interestingly, this is CD equal to CDI condition. This is actually max endurance. That's why I remember that. This is a condition for maximum endurance for flight mechanics because CD equals CDI. Okay. So, any question here today? Let's stop here today. So next class, we're going to bring X5 demo, and then I'm going to completely videotape, and then we're going to videotape the other section to finish up this unit D1. All right. Yeah. What's up?
If you go down to the graph.
All right. Have a good day. See you guys on Wednesday.
Can I see also the demo?
Yeah. My notes are great.
I just need to copy them.